You see these headlines all the time, right? Coffee helps you live longer, or screen time is linked to anxiety. We're just constantly bombarded with these claims. But how do we know if the connection is actually real, or if it's just some random coincidence? Well, today, we're going to pull back the curtain and look at the statistical tools that help us see the real story behind the numbers.
And really, that's the core question, isn't it? When you see a chart or some data that seems to show a pattern, how can you actually be sure? Thankfully, statistics gives us a way to measure these relationships, to go from just a gut feeling to a real, quantifiable connection.
All right, so let's get into it. Our first and maybe most basic tool is called correlation. The easiest way to think about it, it's like a statistical ruler. It just measures how two things move in relation to each other.
Now, the two key words here are size and direction. See, correlation doesn't just tell you if two things are related, it tells you how they're related. Do they move together, or do they move in opposite directions? And maybe just as important, how strong is that connection? Is it super strong, kind of weak, or just somewhere in the middle?
So the way we measure this is with something called the correlation coefficient, or R. And it's actually really straightforward. It's just a scale from -1 to +1. If you get a +1, it means they're in perfect sync. When one goes up, the other goes up. A -1, that means they're perfect opposites. And a 0, well, that means there's really no linear relationship to speak of.
Okay, so knowing that two things move together is great. That's a good start. But what if we want to know how much the change in one thing can actually explain the change in another? Well, for that, we need a more powerful tool. And that's where something called R² comes into play.
Now, the official definition might sound a little academic, but trust me, the idea is really simple. The dependent variable is just the thing you're trying to explain or predict. Let's say a student's final grade. The independent variable is the thing you think is doing the explaining, like, say, the number of hours they studied. R² just tells you what percentage of those final grades can be explained by all that study time. So let's say a study comes back with an R² of 0.7, or 70%. What that's telling you is that your model, the factors you decided to measure, accounts for 70% of what's going on. The other 30%, well, that's due to other stuff. Things you didn't measure, maybe lurking variables or just random chance.
Here's another way to think about it. Imagine you're looking at a bunch of data points. You could just draw a straight line right through the average of all of them. That's your baseline guess. R² basically tells you how much better your special best fit regression line is at explaining the data compared to just that simple average line. It's a measure of its explanatory power.
So here's the bottom line. The closer that R² value gets to 1, or 100%, the more of the story your model is telling. A perfect R² of 1 means your model's predictions line up perfectly with the actual real-world outcomes. It's a perfect fit.
Okay, that's enough theory for now. Let's make this concrete with a real-world example. So there was this university statistics instructor, and she had a question. Do the optional homework problems she assigns, do they actually help students get better final grades?
So she tracked 12 students, and what you're seeing here is a chart of the results. Along the bottom axis, you've got the number of homework problems they completed, and on the vertical axis, that's their final course grade. I mean, you can kind of see the pattern just by looking at it, right? As the dots move from left to right, more problems done, they also tend to go up, higher grades. So they took this data and ran the numbers to calculate the R², and the result they got was, well, it was surprisingly high, 78.4%.
Okay, so what does 78.4% actually mean in plain English? It means that for this specific group of 12 students, almost 80% of the variation in their final grades, the reason some did better and some did worse, could be explained just by looking at how many of those optional homework problems they completed. That is a really powerful connection.
But, and this is a huge but, this powerful connection brings us to what is maybe the single most important, most vital, and honestly most misunderstood rule in all of statistics. And it's this. Just because two things are strongly correlated, it does not mean one causes the other. I'll say it again. Correlation is not causation. And this right here is the perfect example to show the difference. On the one hand, you have a statement like, smoking causes an increased risk of lung cancer. That's causation. We have mountains of evidence to prove that. But on the other hand, you have higher ice cream sales are correlated with higher sunscreen sales. That's not causation. That's just correlation.
So why are ice cream and sunscreen sales linked? It's because of something called a lurking variable, a hidden factor that's actually driving both things. And in this case, it's pretty obvious, right? It's hot weather. The hot weather causes people to buy more ice cream. And the hot weather also causes people to buy more sunscreen. The two things move together, but one doesn't cause the other. It all comes down to this one critical phrase. If you remember one thing from this, make it this. Correlation does not imply causation.
All right, we're almost there, but there's one last, really important detail we need to talk about. Because as powerful as R² is, it has this tricky little flaw. It's a problem that statisticians sometimes call the kitchen sink problem.
So, imagine you're building that model to predict student grades again. You start with homework problems, okay, that makes sense. Then you add in hours of sleep. Then you add their favorite color, then their shoe size. You're literally throwing in everything and the kitchen sink. Here's the problem. Your R² value will never go down when you add more variables. In fact, it'll probably tick up a little bit, just by pure chance, even if the things you're adding are total nonsense. And this can make a really weak model look deceptively strong.
So how do we fix this? How do we get a more honest number? Well, we use a smarter metric called adjusted R². It's basically a modified version that penalizes the score every time you add extra variables that don't genuinely improve the model's predictive power. Think of it like R² but with a built-in reality check.
And if we go back to our homework and grades example one last time, you can see this in action. The regular R² was 78.4%, but the adjusted R² was a little bit lower, at 76.2%. That small drop is the adjustment, and it gives us a much more honest, more conservative assessment of how strong that connection really is.
All right, so let's do a super quick recap of the key takeaways. First, correlation just shows if two things tend to move together. Second, R² takes it a step further and tells you how much one thing can actually explain another. Third, and this is the big one, the golden rule, correlation is not causation. And finally, if you want a more honest metric, you should always look for the adjusted R².
So we'll leave you with this final thought. The next time you see a headline or a study that claims X is linked to Y, you now have the tools to think a bit more critically. So, what's the first question you're going to ask yourself? Is this a real causal link, or is it just a correlation with some other sneaky, lurking variable hiding in the shadows?